Good afternoon, everyone. Welcome to our session for today. Today, we're going to continue our discussion on the time series analysis using ARIMA, Autoregressive Integrated Moving Average. I sent you a file in Canvas, and instead of using here in line 13, instead of using Apple stocks, we're going to use the Bud Light stocks because that's very interesting. Also, please take note that I already, let me just check. I don't know if you have already written your names here. Where's that? Finlitz. Okay, here. Finlitz K32. And worksheet number 2. Here, case 1, RRL. Okay, only 3 groups have written their names. Okay, so the rest, please do that. Kindly already write your names in the groups, and then please write your topic title because I'm going to approve this. So the soonest attendance mamaya na lang, the soonest possible time you're able to write it for my approval. Okay. So if you write here cash light economy, kailangan yung topic mismo, hindi pa pwedeng generic lang na topic. You cannot write blockchain or cryptocurrency. Hindi pa pwedeng ganun. Kailangan yung specific na topic. Okay. So I leave that class. You have kindly within the day, kindly make sure that you already write your group here, and then hopefully by tomorrow you have already written your topic title. Okay, so let's go back to R. Okay, so what have we done so far? We have had our introduction to time series modeling using ARIMA process, autoregressive integrated moving average. Last time we said that autoregressive AR process, autoregressive, models your time series based on past values of itself. I have given here for your notes, the one that I'm sharing with you now, some very good references. Now these are references that I suggest that you look at. There are of course many other references. You have so many to choose from in the internet, aspects about the AR process. So I leave you guys to choose, but this one are recommended ones. These are just a few of the so many good references there. Now I'll give you a few minutes, maybe 2 minutes, 3 minutes to load. Okay, I'll just remove the tidyverse here. Load these packages. You know the drill, class. If it does not load, it means that the package has not yet been installed. Then you will have to use installed packages first before you use library. Okay. And once you're done, kindly chat yes, please. Kindly chat yes in our chat box. In the meantime, I will pause recording first to give you time to load the packages. So these are the packages that we're going to use in the course of this session. Not today, but in the succeeding sessions. So I wanted you to already load these packages. Quant mode, we'll be using that for downloading stock prices. ggplot2 for plotting. Urca later on also for Garch processes. Okay, TSM for time series modeling for ACF and PACF. All right, so if you usually you'll get messages like this. Okay, it simply means that when you load a particular package, sometimes other packages are loaded also with it. So for example, forecasts per, when you loaded the tidyverse, okay, tidyverse, did I put tidyverse here? Okay, when you load tidyverse, I'm wondering why. Did you see this this message also, class? Kindly chat, please, if you see this message from R. Okay, my screen is sharing, right? Okay, so sometimes you'll get messages like this, like attaching core tidyverse packages like forecast, per, read R, string R. It means that these are packages that come also loaded when you load a particular package. For example, when you load tidyverse, it will automatically also load ggplot2, dplyr, readr, per, and other packages with it, lubridate, etc. So some packages get loaded when you load a particular package. What's important for us is this message, tidyverse conflicts. So for example, the function filter comes, it's used in plotly package and also in time series package. So if you're going to use the filter, okay, the filter function, without any qualification, it will come from the filter function of plotly. So if I need the filter function coming from time series, then I will have to write this. This will be my function, time series and then double colon filter. Okay, if I want to make use of the function filter coming from time series, and I write my code here. Okay, now this is because if I just use filter, okay, what will happen is that the filter function coming from plotly will be the one that's run. Kaya sabi dito, it masks. No? It masks. Also, yung plotly filter also masks the filter not only from time series but also from dplyr. Si dplyr din merong filter function and also si stats function. Okay, so if you want a particular function like this one coming from a particular package. So kunyari, ang gusto kong, what I want is the dplyr, the filter coming from the dplyr. Then I'll have to write this one, dplyr, and then double colon filter. Okay, so that's when you'll be able to make use of the function of filter from dplyr. Same thing here, the XTS, the first function here, will mask the dplyr function, etc. Okay, so that's just a warning. That's just information that we need, especially if you're going to make use of these functions, as I mentioned a while ago. So kunyari, you're going to make use of the interval function coming from lubridate. Then you will have to make sure that lubridate, okay, is written lubridate, then double colon, then interval. Okay, otherwise, failure on your part to do this will make use of the cbol function, cbol package, the interval function, and it might not be the one that you are interested in. Okay, so I hope that's clear. Just be wary of messages like this coming from R. Okay, now last time we discussed about loading TSM. I think there's no more problem. I think we discussed that. So hopefully your TSM package is already installed, and you can check if you go to package and then type here TSM. You should be able to see that TSM is already loaded, and then it's checked. It's already checked because we already wrote library. There you go. So just to verify. Okay, and then we said last time that there are several methods in modeling time series. We distinguish between what a time series data is from a cross-sectional data and from a panel data. For time series data, okay, we're looking at one unit across several points in time. Okay, and how do we model this? We're just taking a look at one unit. So it's a univariate. Okay, so let me just put here univariate time series. When I say univariate, okay, I'm just looking at one variable. Okay, it may be the sales of we may be looking at sales, we may be looking at, let's say, revenues, or we may be looking at stock prices. But we're just looking at one. We're just modeling one. You might have several variables, let's say you can have several data, but we're just modeling one particular variable. Okay, and we said that we can make use of the Box-Jenkins approach. This is one of the most powerful methods. However, there are some rules that we need to follow when we use this model. Okay, and we defined last time what an AR process is. AR, we said, was a methodology where we use the past values of the data itself, of the time series itself. And MA makes use of the past error terms. And I stands for integration, which means differencing. Okay, and we gave an example of what an AR1 model is. We said that an AR1 model seeks to model, okay, model our time series. So this is our time series, X sub t. This is our X sub t. And we model the AR1 process. Okay, the main component here is your X sub t minus 1. Okay, so you're regressing, you're modeling your X sub t based on its past values. And then there's this coefficient here. Then we add a certain constant, and then the error term of the current period. Okay, so that's an AR1 process, autoregressive. As we said last time, autoregressive means you're regressing, you're modeling your value based on itself, past values of itself. Okay, so it's very easy also to understand what an AR2 process is. So by the way, now there are certain assumptions here that we have to remember. Every time we model, we will have to test whether these assumptions are followed, are complied with, or are violated. This one, the error term here. This is the nature of the error term. Okay, the error term should be individually and independently distributed, normally distributed, okay, with zero mean and constant variance. This is your variance, okay, constant variance. So this should be how your residual, your error term, will behave, okay? So, wait. Okay, so we also looked at what an AR2 process will look like. Well, as the name suggests, autoregressive order 2. Okay, order 2, which means that you have lag 2 and lag 1. So these are your coefficients, phi2 and phi1. Now, you have to research, class. There are certain conditions about phi1 and phi2. It's not something that phi1 and phi2 can take on any rational value. Hindi pa pwede. There are certain parameters, there are certain restrictions, or there are certain rules where phi1 and phi2 are in a sense limited. Okay, there are certain rules that about the values of phi1 and phi2. Okay, any questions about an AR2 process? Let me pause for a while. And may I ask you to please chat in the chat box if we're clear so far. Yes, we're clear. And in case you have any questions. Okay, thank you, Abijah. Clear, thank you, Greco. Okay, I would appreciate others also. Althea, Jerome, good, thank you. Please don't hesitate to ask your questions. We're here to learn, okay? We're here to try to clarify if there are any misconceptions or any things that you don't understand about my discussion. Okay, thank you. All right, so this is your AR2. Generally, your ARP process, the P stands here for the log. So you can denote generally an AR process of log P as, again, this is the constant, and then we have phi1 times log of 1 plus, and then here is P minus 1, phi sub P minus 1 times log, that's P minus 1, it's always T minus P minus 1, and then T minus P. This is phi sub P, and then the certain error term. This one. Okay, so this is an ARP process with P logs. This is your T minus P. This is phi sub P. This is the Pth log. Okay, and then we discuss also what an MA process is. MA refers to the error terms or the residuals. Sometimes it might be better, instead of modeling your time series based on the actual values, actual log values, maybe it's best to model it using the residuals, the error terms. Okay, so an MA1 process will look like this. There's also this constant. Here we're using mu instead of delta for AR process. So mu plus the error term plus theta1 epsilon sub t minus 1. Okay, so here we're using theta, while in the AR process we're using phi. And then also we have MA2, which is, again, the constant plus your error term plus log1 error term plus log2 error term with their coefficients. There are also parameter requirements as far as the values of theta1 and theta2. For example, theta1 and theta2 cannot be more than 1. Okay? They cannot be more than 1. And also, there are also requirements as far as the sum of the coefficients. Okay, we'll discuss that as we go along, but I would that you already research on that. No? What are, for example, AR1, yung phi1 na yan. What's the, are there any dimensional constraints for that? So for example, the phi1 cannot be more than 1. Okay, the phi1 cannot be more than 1. It has to be less than 1. Okay, that's one of the constraints as far as the value of phi1 is concerned. Okay, so let's discuss that as we go along. Okay, so MA1, you have this, right? Theta1 times epsilon t minus 1. This is log 1. Or if you have MA2, you have theta1, theta2. Theta2 is epsilon sub t minus 2. Or if you have the MAQ, so there are, okay, I'm not sure if you got here W, all the E's should be epsilon sub t. So just kindly change that, class. In the other section, what I sent was, there was a mistake in my variable because it was written as W. So this is the correction. What do you get, class? Is it a W or an E? Class? Okay, okay, E, no problem. Okay, good. All right. Now, if you combine both, say you have an AR process and an MA process, you call it an ARMA 1-1. How will the function look like? How will the equation look like? Well, this is your P component, right? ARMA P, Q. The 1 refers to your P. That's the log of AR. And the Q is also equal to 1. That's the log of MA. So the equation will be x sub t is equal to a certain constant. So we're not using the delta or the mu because this is now a combination of your AR and your MA component. So let's just use C plus Phi1 x sub t minus 1 plus epsilon sub t plus theta 1 epsilon sub t minus 1. Okay, so that's our ARMA 1-1 model. Okay, any questions so far? Again, sorry if I keep on asking these questions. I just want to be sure that I'm getting, you're able to understand what I'm saying. Okay, so far clear about the ARMA 1-1 process class? Okay, good. All right, then how about an ARMA 2-1? So an ARMA 2-1 will just be log 2 of your AR process. So take a look at this, x sub t minus 1, x sub t minus 2. That's phi1 and phi2. And then you have one log for your moving average. All right, may I ask the class? Okay, kindly write in the chat box what type of ARMA model this is. So you type ARMA, then open and close parentheses. What's the model here? So I'll wait for your, wait, huh? So let me, so kindly write ARMA and then open and close parentheses. What will be the log of one of the AR and your MA? For that equation? This one. Okay, only one so far has answered. How about the others, class? Waiting for your answers. ARMA 22 from Ishan. Thank you, Ishan. How about the others, class, please? I see only Ishan answering. How about the others? May I have your inputs, please? ARMA 21 for Rachel. Only two have answered so far. How about the others, please? Okay, thank you, Ishan. Thank you, Abidja. Okay, sino po ba? Jerome, salamat. Okay. All right. So the answer here, class, is this is an ARMA 2-1 process. 2-1, no? Why 2-1? Why 2-1? The highest log of your AR process is 2. So this makes it an AR2 process. Now, is it still an AR2 process even if there's no existing x sub t minus 1? Yes, class. Because the AR process will take on the highest log. Okay, it simply means that your t minus 1, your first log, is not significant. Okay, the phi1 x sub t minus 1 is not significant. And this one is, of course, this is your epsilon sub t minus 1. So that makes your MA1 component. So taken together, this is an ARMA 2-1 process. Okay, I hope that's clear. Okay, and then we have here combination. I think this is where I made the mistake. I think this is W. So just replace W by E. Okay, for us to generate the ARMA PQ model. And you can see here that the last expression for your ARMA AR process is P. Andito siya, no? Phi sub P. You can find it here. No? This is the coefficient phi sub P, which means that there are P lags. And that signifies the P lag for ARMA. This is standard nomenclature for ARMA. And then also we have theta sub Q. So this is your Qth lag for your MA process. Okay? All right. Now, generally, the model is ARMA PDQ. So this this one, ARMA PQ, is also equivalent actually to ARMA, okay, ARMA. So P lags, letter small, and then 0, and then Q. Okay, 0 means that the time series was not differenced. So ARMA PQ is just the same as ARMA P0Q. The D there stands for differencing the middle letter. And then in this case, since we did not difference, the D here takes on a value of Q, 0, I mean. All right, so now these are the steps. What are the different steps in running an ARIMA process? Okay, number one, class, obviously this is self-explanatory. You plot the data. Okay, plot the data and check if the data is stationary. Now, what does it mean to be stationary? Okay, there are two things here. Stationary in terms of, I think this is just a review. We discussed this last time that, so where's my annotate here? So it means stationary. Okay, in mean and in variance. Okay, stationary in mean, this means that the average of your time series at any point in time is constant. Mean is equal to constant. What does it mean for the mean to be constant? It means that there should be no trend. Okay, what do I mean by that? Suppose this is your time series and this is your data. So you can see here that your data follows a specific trend. Okay, if there's a trend, then if I take a look at this sector here, the average of this time time series here might be this one. No? This might be the average. So for this segment, for this period, okay, the average of your time series is this amount. However, when we go here, okay, so this might be the middle figure here. Okay, so this might be the average. Okay, so I hope you get what I mean. So you notice now that the average here, which is this one, is not the same as the average here. Okay, so because of the trend, the average for specific periods of the time series are not equal. The mean is therefore not equal to 0. Okay. Sorry, it's not constant, I mean. So the mean can be equal to 5, it can be equal to 10, but it means that it's 10 all throughout. Okay. It means it's equal to 5 all throughout. If at certain points in time, the average is, let's say, 5, and here it's equal to 8, and here it's equal to 12. So you notice that there is an increase in the averages. So that means that your mean, the average of your data, is not constant. Okay, therefore, it's not stationary in mean. Now, on the other hand, for stationary invariance, there might be no trend, no? The average, okay, possible na yung time series natin, okay, actually here, it does not have a trend. Merong fanning out ng data. Okay, the data seems to be increasing, no? At least the range niya, the variance. Kasi if we take a look at this one here, at this point, class, ang variance niya, the difference will be this one. But at this point, diba? Ito yung variance niya. And it's bigger than this one. Okay, so not constant yung variance dito. All right? Let me clear once again. Okay, class, is this clear so far? Yung stationary, yung concept ng stationarity. Okay? So, in ARIMA, you cannot model a time series that's not stationary. It has to be stationary because of the characteristics of your phi1, phi2, theta 1, theta 2 of your predictors, of your coefficients. Okay, so now if they're not stationary, you have to do something. You have to transform your data. Okay, why do we need to transform the data? Because if you do not transform your data, then you cannot make use of ARIMA. Okay, ARIMA will work only if your data is stationary. So if I don't want to use ARIMA, are there other tools? Yes, of course, maraming ibang tools. But ARIMA is one of the most powerful. Okay, so in order for us to use this, kailangan i-convert natin, i-transform natin our data should be transformed into stationary data. When we say, once again, I hope I don't don't sound like a broken record. Stationary data means the mean is constant and the variance is constant. Okay, if it's not stationary, then you will have to address something. You'll have to transform the data. So how do we transform the data? Well, it depends on the nature of the data. If the data shows trend, if it's like this, or like this going down over time, if it's increasing over time, that means there's a trend. So how do we address the trend? We do differencing. So you difference your data. If it's going down, same thing. You also difference your data. Now, if you difference your data, what happens? Okay, so let's suppose this is your original time series XMT. You have 10, 12, 13, 14, 12, etc. Okay, so if that's your original time series, okay, so what do we do with this? Assuming this is not stationary, it has a trend. What do? We have to difference this data. So what happens is, suppose this is the later data. So it's 12 minus 10, that's 2. And then if this is 13 minus 12, that's 1. Then 14 minus 12, that's 2. 12 minus 14 is 12, okay, etc. So now we were able to generate a new time series. So this, if this is x, let's call this dx. This is now the difference of your x. And if you plot this, most probably your data will now become will become no trend. Okay, because differencing usually heals the trending. Now, if it so happens that the data is still not stationary in mean, then maybe you need to get another differencing. So may ddx tayo kunyari, no? I just call it difference of the difference of x. And then it now becomes 2 minus 1, that's 1. 1 minus 2, that's negative 1. 2 minus, what's this? 2 minus whatever this is, 2 minus 2, that's 0, etc. So you now have another data set, which is different from the original data set. So please remind yourself, be cognizant, be aware that when you're doing differencing, you're not this time modeling the same data set. It will now be a different data set since you difference it. Now, why will I do that? Because if you don't do that, you cannot use ARIMA. You will have to difference the data. Now, what if after you difference, you still have the non-constant variance? It's still fanning out. Then that's the time you also you get the log. So one way to address the non-constant variance is to get the log of the data. Okay, let me repeat that process. Okay, so first you have to plot the data and to see if it's stationary or not. If it's stationary, then okay to proceed already. If not, then you have to check, is the data not stationary in mean? If it's not stationary in mean, then you just difference. Okay, because the differencing will address the trend. Is the data not stationary in variance? It means that the variance is not constant. Then what you can do is get the log. Okay, you can get the log of the data. Okay, where's my, oops. Where's my, naka-on pa pala yung ano ko. All right, so as I was saying, sorry, where did I stop class? What was I talking about? Hello? Hello, class, am I still on? Can you hear me, class?
Yes po, sir.
Okay, so I was talking about the log of the data, okay? Asan yung ano ko, yung, dali ha? Okay, sorry about this. Okay, so if the choices are simple anyway, class. If the data is not stationary in mean, it means it has a trend, then you difference. If the data has no trend, but it is not constant in variance, which means it's fanning out. Okay. The data is not constant in variance, so your data behaves this way. Okay. So it's fanning out like this. Okay. It's fanning out like that, then the variance is not constant. For this particular time frame, this is the variance, but here the variance is now bigger. So when you have this, one of the best remedy, there are different remedies, class, but one of the most simple remedy is to get the log. Log of the data. Okay. Now what happens, class, if your data has trend, it has trend, and the data also has, so suppose it's moving this way. It has trend, and the variance is not constant. So it's behaving this way, class. It's trending up, and then the variance is not constant. Okay, what do we do with this? So two ways. Okay, let's see. Either you get the difference first, step one, or method one, no? M1, you get the difference and then get the log. Or model 2, M2, I'll call it M2, you get the log and then get the difference. Okay, so kindly chat, please. What do you think is the appropriate method, appropriate procedure? Do you get the difference and then get the log, or you get the log and then the difference? Kindly chat, please, in the chat box. M2 for Jerome. How about the others, class? How about the others? What do you think? Is it M1 or M2? M2, M2. So Ishan says it's M2. Abija says it's M2. Luis also M2. Okay, any other answers, class? M2, how about the others? I see only a few answers here. May I get the participation of the other students? Only a few answers? Okay, thank you. Okay, sige. So, Jacob says it's M2. Why, Jacob? Could you please unmute yourself? Mr. Garcia, Jacob, why did you say it's M2? Jacob? Hello, Jacob. Okay lang, sige, i-type mo na lang. Kindly type. Why did you choose M2? Waiting for you, Jacob. What was your reason to choose M2? We're waiting for your chat. What's your guess? Why? Why did you choose M2? You must be coming from a particular for you that there might be a particular reason for that. Hello, Jacob. Guess lang. Okay. Sige, thank you for guessing. Okay, sige, tingnan natin si ano. How about Christine? Why M2? Villanueva, Christine?
Hello, sir.
Yes.
My answer po is log muna and then difference po after.
Yes. Why?
Um, Kasi you can't log the numbers kung may negative numbers pa po. Kaya log
Okay.
bago mag-difference.
All right. So thank you for Christine for that. No? Ang sabi ni Christine, log muna, no? Log muna and then differencing. Let's try, class, getting the difference first and getting the log afterwards. So let's suppose we have a time series like this. No? Kunyari time series natin, 100 and then 98. Kunyari pababa yung 97, then naging 98 ulit, then 96. Let's say that the prices are going down, 95. Okay, so this is yung before. Okay, so this is chronologically arranged. So what will happen is that if we difference first, this becomes 98 minus 100, that's negative 2, di ba? And then 97 minus 98, that's negative 1. 98 minus 7, that's 1. 96 minus 98, negative 2. 95 minus 96, that's negative 1. So we have a time series here that's, at least for this particular period, the value was going down. If we do the differencing, okay, so most probably this might have a pattern. No? The trend might be going down like this. So because of that, class, this one is not stationary because the mean is not constant. Okay, and then if we differentiate negative 2, negative 1, negative 1, positive 1, negative 2, could you kindly run here log log of negative 2. So let's take now, after differencing, so take note, this is difference first, and then log. So if you get the difference and then get the log, could you kindly get the log of negative 2? Kindly, please. Tell me here, dito, i-type nyo dito, log of negative 2. Dito na lang sa console. Here in the console, type log negative 2. Tell me what value are you getting? Okay, thank you, Vincent, thank you. Yes, thank you. Abija, thank you. Okay, yes. Thank you so much, class. Now, what happens is that not a number. You produce this result, not a number. Why? Because you cannot take the log of a negative number. This one means if the base is 10, but here the base is 2, no? It means that e to the x, what number, okay, what number, when you raise by e, okay, so what is the value of e of x, so that if we raise it uh, uh, by e, will give us a negative 2 answer. Okay, to make it more to make it clearer. So if I'm getting the log of negative 100, okay, and then I type base is equal to 10. Okay, because in R, log will take on the base of e, number e. So if I type log negative 100 base is equal to 10, could you kindly type that here, class, and see what happens? What do you get if you get the log of, so log here, log, okay, log a log of negative 100, then base is equal to 10. What will I get out of that? Enter. Okay, this is not a number. Okay, but if I type log, if I ask Excel to R to get the log of 100 to the base 10, okay, base is equal to 10, control enter, that's 2. Because if you recall from your algebra, the log is, how is the log defined? It's that number, okay, the base 10 here. So x is equal to log, just a review of log 100, and in R, let's say you're using the base 10, okay, but in R, when you log, class, automatically the default is that you're basing it on e, okay, so this is natural logarithm, to be exact. So what does this mean? Base 10, so that means what is the value of 10 raised to the x such that the value will be equal to 100? So you know the value here is 2 because 10 raised to the 2 is 100. However, the first problem, 10 to the x is equal to negative 100. You cannot find a value of x so that if you multiply 10 by itself for x number of times, you'll get negative 100. Okay, that's not possible. So it's non-existent. Okay, so for the log, the range of the value should be all positive numbers. Okay, all positive numbers. So you cannot get the difference first and then get the log, because if you get the difference, chances are you might have negative values. Okay, so if you have negative values, you cannot get the log of that. So the process is first to get the log and then get the difference. Okay, and when do you do this? You do this when there's non-constant variance and non-constant mean. Okay. Clear so far? Gus, kindly request you to please give your feedback if it's clear. Okay, thank you. Waiting for the others to give their feedback. Okay, good. Thank you so much. All right, class. So in your cases in the future, if you're asked to model using ARIMA, you have to first, again, the first step is to plot the data, have a visual inspection of the data, and then see if it's stationary. Okay, if not, then you will have to do some transformation, either get the difference only, or get the log only, or get combination of this by getting the log and then the difference. Okay, so that takes care of these steps. And then after you difference, class, after you transform your data, you difference, or you take the log, or you take both processes, what happens? What do you do? Okay, by the way, before I, I leave this, when you difference, class, ito yan, ano? PDQ. This is the order of your AR process. This is the order or lag of your MA process. This is your differencing. Usually, you just do one differencing. Okay, that will already address your non-constant mean. Okay, but sometimes there might be a need for double differencing, especially if you're dealing with seasonality in your data. Okay, so you might have double two differencing, one for the regular and one for the seasonal. What do you mean by seasonal differencing? Suppose you're dealing with sales of flowers. Okay, you're dealing with sales of flowers. Usually, flowers sales go up. Let's say this is your time series. It may go up during February, and then go up during November, and maybe December. Okay, you can see here that these are the peak months: February, November, and December. Flower sales might go up. Okay, so there's a trend for this. The sales is generally going up, but also there's a trend as far as seasonal component is concerned. Every February, so this process is repeated. Next February, you have this one. And the next October, you have November, you have this one. And next December, you have this one. So notice February and February, okay? There's a trend also for February. There's a trend for November. There's a trend for December. So prices were going up during those months. So you have a two-tiered trend here. One is for the general trend, okay, and the other one is for the trend as far as a particular season is concerned. So that's seasonality. So in this case, there might be two differencing. Possible yun, no? That might be possible. But third differencing, most probably not. I haven't met because a model where there was three differencing. The biggest differencing that I saw is a differencing, second differencing. And take note, class, once again, that when you difference your data, okay, let's suppose your data is X. Okay, so we have, okay, use this. Our data is X. Then when we plotted our X, this is our X sub T. When we plotted our X sub T, we noticed that there was a trend. So we difference our X sub T. Okay, now take note that your difference X sub T is no longer your X sub T. And then let's have another difference. I'll just call it difference of X sub T. So I difference it twice. So maybe this data set has seasonality also, trend in seasonality. So that's why we had to difference it two times. And let's suppose that what we did was to get the log of the data. So we actually were using log of xt. So this will be the difference of the log xt. This is the difference of the log xt. Okay, log of your time series. So this data class is not the same as this one. It will be very, very different. Okay. But when we model this, we come up with a model for DDL xt. And then we can predict this. Okay. So the predicted values are not the original values that we want. So the predicted values are the double difference log of xt. Now, what we want to forecast is this one, the original data. So what do you do? Because you're getting values here that are not incongruent or are not the same, are not consistent with your original data. And what you set out to model in the first place was the original data. But because you're using ARIMA, you have to do transformation, and you have this. Okay, so no problem. You can actually reverse the process. You can actually convert this back into the original. Okay, we're going to look at that in the future. So as I said, going back to the what we have in mind, we want to predict the sales, XT sales. No? Okay, so let's suppose that this is our model, double difference and log XT. Then we will have to remove the log. We will have to remove the differencing in order to go back to the original XMT. We'll have an example of this. Okay, are we clear so far? Kindly please chat. Okay, good. Okay, good. All right, then, okay. Thank you for your answers. Okay, now that we have, okay, let me close my annotation. Okay, what have we done so far? We looked at our data. It's not stationary. It's not stationary in mean, not stationary in variance. So what we did was to get the log of the data and then get the difference of the data. Okay, then we were able to convert and we plotted the data, and then we saw that it's stationary. Okay, so what to do next? We will have to check, although visually it might be stationary already, there's a statistical test for that. We can test it statistically using the ADF test, which is the augmented Dickey-Fuller test. So we're able to really test statistically, hindi lang by visual, no? Okay, what's KPSS test? Anyone, please? I-Google nyo ano yung KPSS test. Kwiatkowski, Phillips, Smith, and Shine ba yun? Okay, so these are 4 statisticians. Can anybody please? Kwiatkowski, ang hirap. Ayan. Thank you. Kwiatkowski, ang hirap i-pronounce ng name. Phillips, Mead, and Shin. So these are the 4 statisticians who developed this test, KPSS test. And what's this used for? This is to statistically test if your data, in particular the transformed data, in our case, example natin yung double difference tapos log transformed data, if it's already stationary. Okay, so we don't necessarily just trust on our visuals because sometimes that can be difficult. There's a statistical test for that. Yan, sinulat ko pala dito, no? Okay. See, Phillips, Mead, and Shin. Okay, the next. Okay, now, all right, I might have to, okay, let me see. I might have to stop at a certain point before the class and kasi kanina, I'm sorry, I made a mistake, no? I got confused a while ago, but none of the students told me. We were supposed to meet from 11 to 12:30. And then na disorient. Kasi 12:15 na. So I thought hanggang 12:15 kami. Yung pala itong 2:15 yon. So sabi ko, okay, 12:18 na nun, nag-apologize pa ako sa kanila na nag-extend ako. Wala naman nagsalita sa kanila. No, not one of them reminded me that the classes was until 12:30. Okay, anyway, so we reached this far. Okay, so we will have to understand what this is, the autocorrelation function and the partial autocorrelation function. Now, this is very important in order to determine, see, okay, where are we now in our steps? we have concluded that our data is stationary, then we can now proceed with determining what model are we going to use. Is it an AR process? If it's an AR, is it AR1? Or is it AR2? Or is it an MA process? If it's an MA process, then is it MA1, MA2, or is it an ARMA process? Is it ARMA 1.1, ARMA 2.1, ARMA 2.2, etc.? Okay, so that's now what we're going to determine. Okay, we're going to now determine what type of model are we going to use in order to model our time series. Now, how do we do that? Okay, this is where the ACF comes into play. So the ACF and the PACF, this means autocorrelation function and the partial autocorrelation function. This is very important to determine whether you are doing an AR process or an MA process. Okay, so you identify the best fit ARIMA model based on AR and MA. Now, however, this was before. No? This was before when there were no packages, softwares like R. Because when we were doing this during our time, we will have to generate the ACF and the PACF manually. And this can be very difficult. This can be tedious. And then once we have plotted the ACF and the PACF, we will have to determine if it's an AR model or an MA model based on the ACF and the PACF plots. Okay, and that will be only an educated guess. Then you will have to do some iterations, other guesses, and then what you're going to do is to compare. Kunyari, if for example I thought that this is an AR1 process, and then I compute for the equation for AR1, okay, and then maybe it's an AR2 process, and then I compute for the AR2, and then I will compare which of the model is better. Or what about MA? Is it an MA process? So after I generated my AR process, I also generate my MA1 process, and then I compare by looking at the residuals. So this is a very tedious model class. So one data set can take you 1 day because the process is quite long. So the steps here, actually, they more or less look at this from a manual perspective. Because nowadays, class, this one, the plotting of the ACF can easily be done just by one line of code in R. Okay, and then the identification of the best fit model can just be run just by one code in R. So one code, and then you're finished. Imagine being able to do the model in 3 minutes to 5 minutes, while during our time, we had to model this 1 day, okay, just for one model. So if you're able to create a model for just 3 to 5 minutes, then you can model several time series. Okay, so that's the advantage of the use of technology. All right, then, okay, am I clear, class? Am I clear about the use of technology? That's why you're very blessed at this time. Kasi kayo, in your case, you never had to go through the process of doing the manual approach. Let me pause for a while, class. Feedback. Clear so far? Are we understanding the ACF and the PACF? All right. Thank you. How about the others, please? Okay. Notice that we haven't actually started writing a code. On Wednesday when we meet, on Tuesday when we meet, I hope you'll please bring this for those of you who can bring your laptops, because we're going to continue this. And the next portions here, class, this one, this is the code chunk. And then notice here that there's no code here because we're the ones going to write the code. Okay, so because many of you are starting with R, we will have to do some code crunching here. So let's learn by doing it ourselves. Okay, everything here is blank. You don't have the codes here because we're the ones going to run the code. We're the ones going to write the code. Okay, so now, what now do we do? Step number 7, after we have checked we have identified the model, the best ARIMA model, we can also, here we can also plot the ACF and the PACF of our model. Okay, so we generate one ARIMA model, and then we can plot the ACF and the PACF. And you will see the difference between the ACF and the PACF of the original of the time series that we were modeling, and also the model. You will see a difference, which we're going to discuss as we go along. Okay, and then of course we just don't model. We would want to forecast. As I said, this might be sales, and we would like to create a model so that we will be able to forecast sales. And thus, if we're able to forecast sales, we may use this as an input for strategic planning, for operational planning, and use this for operational planning, which means based on these sales, how much raw materials are we going to need, how much are we going to import, how much are we going to access locally, etc. So this forecasting process could now be a key input to decision making. Okay, so that's the role that that forecasting modeling plays. Very important, especially if you have a time series that's really very erratic. Okay, very erratic and quite difficult to forecast. ARIMA is a very powerful one. So you forecast the time series using the best fit ARIMA. Okay, as I said, plot the ACF and the PACF for the residuals. Okay, to try to see if our model is okay, because this will form part of our diagnostics. We just don't come up with a model and say it's finished. We will have to test if if our model stand up to scrutiny by looking at the diagnostics for the residuals. Okay? All right. So I think here I just gave you some notes, okay, and some references. As I said a while ago, stationary time series, statistical properties are the mean, variance, autocorrelation are all constant over time. Constant mean, constant variance. That is, it has the property that the mean, variance, and autocorrelation do not change over time. Constant over time means it does not change over time. So a stationary data looks like flat, a flat-looking series without trend, constant variance over time, and a constant autocorrelation structure over time. Okay, so let's see. If you kindly Control C, copy this link, Control V. Let's see. Just the plot of a stationary. Okay, this one class is a stationary time series. You can see. Okay, and all usually class on time series, it's plotted using a line plot because the data are chronologically arranged. So this is stationary time series. You can see that there's no trend, and the variance seems to be constant over time. Okay, this is the width. Okay, it's not increasing like this over time, neither is it decreasing over time. Okay, so that's your stationary time series. This is your non-stationary time series because it's not constant in mean. Okay, at this point, from this point to this point, non-stationary in mean, the variance seemed to be stationary. However, from this point to this point, there was a change in the trend. It's now going up. And also, there seems to be also seasonality here. And maybe the variance was not also constant here. So you can see here two different periods. Okay, for some, they might decide to model this separately. Okay, that can be a possibility, model this separately. But what we want to point out here is that the time series is non-stationary, in mean at least. Okay, I think these are just two plots here. All right. Okay, let me go back to my, where's my R? Okay, this is also another discussion here. Okay, let me open this also. Control C, and then let me open this reference. Okay, stationary and time series analysis. You can see here a stationary time series, a non-stationary time series. Same lang. Maybe this one. Here. Okay, I click the plots. Okay. I should have used this, no? There are plots here. I saw the plot a while ago. Here. Okay, you can click this. And then this one gives us detecting stationarity and time series data. Okay, so these are different plots. This one definitely is not stationary. There's trend. And then this one seems to be stationary, except for this one. There seems to be a huge spike here. Okay, this one, quite difficult to say this might be stationary or not stationary. The good thing, what I want to point out here is that sometimes visually it can be difficult to determine if a time series is not stationary. Definitely this one is not stationary. This one definitely is not stationary. This one, it can be quite difficult to assess. But good thing is that, as I said, there is this ADF test, augmented Dickey-Fuller test, and Kwiatkowski, KPSS test, Phillips, okay, KPSS test class. All right, this is an example. I'm sorry I wasn't able to show you. ACF autocorrelation plot, and these are both ACF plots, no? Autocorrelation plots. Okay, this is the autocorrelation plot for Google 200. Take a look at this, class. Autocorrelation plot for difference Google. So you notice their autocorrelation is very much different. This one is the actual raw data. This one is the difference data. So differencing has an effect on autocorrelation. That's what I want to point out here. Okay. All right. So let me go back to our discussion. Okay, you need to also understand what we call a white noise. Okay, a white noise series, which is a stationary series. In general, a stationary time series, as I said, will have no predictable patterns in the long term. Time plots will show the series to be roughly horizontal, although some cyclical behavior is possible. When you say cycle, class, cycles are quite difficult to predict or to observe, because cycles, unlike seasonality, which occurs in shorter time periods, for example, it can be monthly, it can be weekly seasonality, but cyclicality is difficult to predict because it seems to be a repetition of a pattern over long periods of time. So it can be a 5-year cycle, and then the pattern of that 5 years seems to be repeating. That's what we mean by cyclicality. Okay. All right. So most of the statistical here, class, are based on the assumption that the time series can be rendered stationary, okay, or stationarized through the use of mathematical transformations. Okay, and here, class, why do we have to convert our data to a stationary data series? Because when you have a stationary data class, it's relatively easier to predict. So that's the main purpose. The reason why we convert a non-stationary data into a stationary data is because it will make it easy to develop a model for it. Okay, you simply predict that its statistical properties will be the same in the future as they have in the past. Okay, the predictions for stationarized series can then be untransformed. This is what I was saying to you a while ago. So we're working now with a different data, but what we're interested in is the forecast of the original data. Then we just unpack what we have done in the past. Okay, so if we did the differencing, we will now do the adding. Okay, so that's what we do, and that can be easily done in R. If we have done the log, then we will do the exponentiation in order to convert back our forecasted values into the original values. That's very easy, class. Okay, so here we transform it by reversing whatever mathematical transformations were previously used to obtain predictions for the original series. All right. Okay, so we begin next meeting, class. Kindly bring this. We'll begin with this line. We're going to we will use the the Budweiser data because Apple is already it's already familiar. So I want us to study what happened to the Bud Light. Okay, so just quickly before we end. So for example, I just want you to do some readings about Bud Light. They just stopped buying Bud Light. Okay, bakit kaya ito, class, no? Okay, it's very interesting since they tapped this transgender si Dylan Mulvaney. Tapos nag ano siya ng advertisement na about Bud Light, and wow, it exploded, no? Alam niyo yung social media ngayon, it's quite easy to for people to react, no? Bud Light is now selling for less than water in some US where imagine less than water yung Bud Light, ba? Okay, let me just share this link with you. Control C. Okay, you might kindly save this. Sorry, kindly save this link so that you may read on that. Okay, this is a good analysis for strategic management and also for finance, class. Although we're not going into the strategic management or marketing aspect of this. So kindly read this and see what happened to, of course, there are many other references, okay, and many other articles written about that. Okay, so let me stop recording now.